Hello. We will be learning about hypergeometric distribution. So what is it? There are two properties we need to know. One is sampling without replacement from a finite population. Basically, it means hypergeometric distribution is dependent. If you pick something from the population, it's gone. And this will change the probability, unlike the binomial distribution, which is independent. You see the keyword without replacement, which is the keyword that separate them both. So one of the example provided are drawing cards from a deck without putting them back, quality inspection where you take items off the production line, and lottery draw where each number can only be picked once. I think you get the idea here. All of them are all of them are dependent. Property 2 is the population has exactly k success and n minus k failures. What it means is you know exactly how many success exist in the total population before sampling. For example, in a card game, a deck has 52 cards. This is total population, so n is equals to 52. From here, we know there are 13 hearts, so that makes it k equals to 13. Again, according to property 2 of hypergeometric, we know exactly success or the things we want to observe here, which is the hearts. While the others, which is non-hearts card, is 39, aka a failure. So n minus k equals 39. So if I want to make it a question, let's say we draw 5 cards randomly. So that makes it n equals to 5. So what's the probability you get exactly 2 hearts? From here, we get the answer using the formulas, which we will get to that later. Again, we're not here to solve the question, but to understand the second property of hypergeometric distribution. I just hope with this example, you get the better idea when to use it. Now, let's get to the formula for hypergeometric distribution. This is the random variable x. N represent the total size of the population, which is the total number of items we're drawing from. K is the number of success items within the entire population. These are the items we're interested in. And n is the size of the sample being drawn. Basically, our sample size of how many items we're selecting. So on probability function, this is the formula we will be using to try and solve the question later. The formula can also be written like this. Depends which one you're more comfortable with. And I forgot to mention that x here, the number of success in our sample. And KCX is the number of ways to choose X success from the K success available in the population. So this is the number of ways to choose the remaining items in our sample from the failures in the population. If we select n items total and x are success, then n minus x must be failures. And there are n minus k failures in the population. This is the total number of ways to choose n items from the entire population of n, capital N items. And finally, when it comes to the x range, it's basically the largest x can be in whichever is smaller between the k and n. Example here, k is 4 and n is 3. Then the x range must be here, which is 2. I know all the explanation can be confusing, So we will proceed to apply it after looking through the mean and variance formula for the hypergeometric distribution. This is the mean and variance, where P is K over capital N, and this is the finite population correction factor, along with this. So okay, with that out of the way, let's look at the exercise. Exercise 1. A shipment contains 18 integrated circuits ICs. 7 of them were manufactured at A and the remaining 11 were manufactured at B. If a quality control engineer randomly selects 6 ICs from the shipment for testing without replacement, find the probability that 4 of them were manufactured at A. Firstly, let's see what information the question gives us. So a shipment contains 18 ICs. So that means N equals 18 for the overall population. 7 of them were manufactured at A. So A equals 7. And the remaining 11 were manufactured at B. So B equals 11. If a quality control engineer randomly selects 6 ICs from the shipment for testing without replacement, so here we get our sample. So N equals 6. Find the probability that 4 of them were manufactured at A. So X equals 4 because it's the item we're trying to find at A, or in other words, our success value. Since it is at A and it's a success, so that means K also equals to 7. Now, if it mentioned, find the probability that 4 of them were manufactured at B, then our K will instead be equals to 11. Just want to give it a mention to avoid confusion. With that, we have all the required information and just insert the number into the equation for hypergeometric distribution. So don't forget the random variable, which is x hypergeometric, and insert the numbers. Using probability function equation, the answer is 0.1037 or 10.37%, if we want it in percentage. So the conclusion we get here is that there's approximately 10.37% probability that exactly 4 out of 6 selected ICs were manufactured at A. Now let's see another example. An incoming shipment of 400 ceramic capacitors from a vendor has been tested, and the quality assurance team found that 30% of them are defective. 1. If 24 capacitors from this shipment have already been soldered onto PCBs, what is the probability that exactly 12 of them are defective? So, we do the same like the previous exercise by extracting the information given. So, an incoming shipment of 400 ceramic capacitors from a vendor has been tested. So, obviously, here it means capital N is equals 400. And the quality assurance team found that 30% of them are defective. So, set of numbers, the question gives us in percentage. But we already know the total capacitor is 400. So, our defective capacitor is 400 times 0.3 due to the 30%. And that makes it a total of 120 defective capacitors. If 24 capacitors from this shipment have already been soldered onto PCBs, here 24 capacitors randomly selected. So that makes it N equals 24. what is the probability that exactly 12 of them are defective? So X is equals to 12. And you see it wants to find capacitor that are defective. So that means the defective acts as our success value. Since it is a success value, K will be equals to 120. In case the question change, so instead of defective, in this case, if it wants, let's say a non-defective, the K value will change to non-defective. So in this case, it will be 400 minus 120 because it is a defective. So K will be 280. Now back to the question. Now we have all the information. So on random variable of hypergeometric, this is it. Using the probability function equation, insert the numbers, and the final answer is 0.01793 or 1.793%. So there's 1.793% chance that 12 capacitors out of 24 can become defective. On question 2, if 18 capacitors from this shipment have already been soldered onto PCBs, what is the probability that more than 2 of these are defective? Here, our data have changed. Capital N, which is the total PCBs, remain 400, as well as K since it asks for a defective. But small letter n, which is a sample, changed to 18. And the rest can just be calculated as per usual. But it's not as straightforward like the previous question, as it wants more than 2. We have gone through this, but I will repeat it again. Since trying to find more than 2 is impossible, because it means we have to calculate it from 3 until 18, which is possible, but we're not gonna do that as it will be a waste of time. So instead, we take a shortcut and take 1 minus px less than or equals to 2. Reasons being, it's the same thing. If you still struggle with this, which is fair, it takes time to get used to it. So I suggest to go watch my other videos from the binomial distribution, as it's also cover the basics like the x more than, less than, in between, and also comes with an imaginary or visual. By that I mean it's in the graph form. So moving on, x less than or equals to 2 means that it's from 0 to 2. So unlike binomial and Poisson, hypergeometric doesn't have a stat table. So you have to do it manually using the equation. Then per usual, using the equation, insert the numbers, and as you can see from here, from 0 to 2, the calculation has become this long. Now imagine if we solve it using using from 3 to 18. Yep, does it worth it just to get the same answer? And for the exam, you can't stay on this question for too long. So the answer we got is 0.05589 or 5.59%. In conclusion, about 5.59% chance that more than 2 are defective. That's all for hypergeometric, and I hope this helps your understanding of these topics. Hope to see you again in our next lesson. Bye!